welcome to Tuesday's edition of Cracking the Cryptic, where I'm probably looking slightly less dishevelled than yesterday. I have had a night's sleep, which is a very nice change after my travails on American Airlines over the weekend. And today I am going to be, well, hopefully in Sudoku heaven, I'm going to be trying a puzzle by the great Phistomefel. I'm a bit behind with Phistomefel puzzles. There's this one, which is called Fare Thee Well, Miss Carousel, a reference, I think, to the Townes Van Zandt song of the same name, which Phistomefel says on Logic Masters Germany has nothing to do with the puzzle at all, except he just likes the song, proving that Phistomefel therefore has excellent taste in music, as well as an excellent brain for constructing Sudoku puzzles. In fact, if I get time, I do know the song a little bit. I'll try and do a version of it for an introduction. That's probably famous last words, but especially in my jet lag state. But anyway, there's this puzzle, which has got 4 stars out of 5 difficulty on Logic Masters Germany. There's a Japanese titled one, which apparently is monstrous, and I have to allow hours and hours and hours to solve, if indeed I will be able to solve it at all. I haven't had a go at that one yet, but I will try it at some point when I have a very long window during the day. And then I noticed he's got a new one as well, which is not a Sudoku puzzle, but it's a sort of logic puzzle, which I'll obviously have to have a go at as well at some stage. And that's only got 3 stars out of 5 difficulty. So anyway, we need to tick off these Phistomefels. So today we're going to try this one. Apologies about the microphone. I am on my old microphone because my usual microphone is in my luggage. American Airlines are claiming that my luggage is now in the UK, which might be true. We'll see. It's certainly not with me yet. So I can just keep my fingers crossed and hope that it arrives at some point. And for that reason, I have got my mobile phone in front of me today, which I very rarely do have. But if it rings, it might be the luggage, and that's going to be too exciting for words, and I will have to take the call. Now, what else can I tell you about before we kick off and have a look at solving the puzzle? Let me just give myself a moment. Over on Patreon, we have got Scojo, Jojo and JoBo's rather wonderful Sudoku hunt as our monthly competition for August. Check it out. The feedback is lovely. It really is lovely. It is a beautiful sequence of puzzles. And you've still got loads of time to enter the competition, which closes on the 20th. There's also my Solve of J. Dyer's repeat prescription puzzle. That is a very hard puzzle indeed. So that's over on Patreon, as well as lots of other stuff too. And then I'm catching up with birthdays. So let me do some birthdays as well. Ben, from your brother Andrew. Ben, it was your birthday on the 1st of August. I'm sorry I missed it. I will, slightly in my defence, say that Andrew's email did arrive on the 1st of August, so that was hopeful indeed. But I would have hoped to have got your birthday before now. But I've been scuppered by many things, Ben, and I hope you had a great birthday with chocolate cake, of course. Next, over in Utah, Lincoln, it's your birthday today. You've turned 19. I know you're studying biomechanical engineering, and also you like my guitar intros. Well, that's good. I'm not sure whether I'll actually get to do any singing if I attempt. Fare thee well, Miss Carousel. You probably don't like that so much, but anyway, Lincoln, many happy returns for today. I hope you get chocolate cake. Matt, is it your birthday today? It might be. You're turning 23. Your brother Nathan wrote and told us, and I think you have a cat called Simon, which I do recall you sent a picture of. It was a very, very handsome cat. My goodness me. But Matt, anyway, many happy returns. And then also turning 23, I think today, is Rose, and I know this because your partner Innes wrote to us, and in a beautiful way described the fact that you were going to have a chippy tea today and maybe cake afterwards. Now, I think a chippy tea, that must mean you're going to the fish and chip shop, right? Have I got that right? That's something. I used to live in the north of England, and we would have a chippy tea if we were lucky. So I hope you enjoy your chippy tea, Rose and Innes, and many happy returns. Next, Beth. This one I'm late with. Beth, I'm sorry. I think you turned 44. Your husband Matthew wrote to us in good time, but during the period where there were troubles, you're over in New Hartford, New York State, if I'm not mistaken, and it was your birthday on July the 29th. And Beth, I hope it was a very good birthday. Ken, it was your birthday on July the 29th as well. And you like very hard puzzles. Well, probably this is probably a very hard puzzle. Phistomefel puzzles tend to be very hard. So Ken, I hope you had a great birthday and you enjoy this video. And Martin, over on July the 28th, it was your birthday, and I know this because your girlfriend Emily wrote to us, and I think the two of you were celebrating in North Wales with family. But Martin, I was disappointed to hear that you don't like chocolate cake, but I was very relieved to hear that Emily was going to eat twice as much chocolate cake to make up for it. Well done, Emily. And then finally, 3rd of August, Paul, it was your birthday and you turned 55. Now, I cannot agree with what you told me about what you were going to eat, which is banana cream pie. There cannot be many things less edible than that. But anyway, Paul, I know you're due to come to London for a holiday for the first time sometime soon. I hope you enjoy that, and I hope you can find some decent cake when you get here. Anyway, that's all the news. Let's have a look. Fare thee well, Miss Carousel, by Phistomefel. That rhymes rather nicely. I will read you the rules of the puzzle. We have got the following. We've got normal arrow Sudoku rules apply. Well, I do know what that means, so I will explain it. So we've got to put the digits 1 to 9 once each into every row, every column, and every 3x3 box. And then arrows, the way arrows work, let's look at this arrow. If this was a 3 and this was a 4, what you do is you add up the total on the arrow, you get 7, so you have to write 7 in the circle. So if this was 6 instead, this would be 9. 3 plus 6 equals 9. So very straightforward. And there's only one more rule, although it's quite a long rule. It says a dot in the centre of a 2x2 square indicates that the two digits in its positive diagonal have the same difference as the two digits in its negative diagonal. This difference is not necessarily the same for different 2x2 squares with dots, and not necessarily all such dots are given. So what on earth does that mean? Well, let's stay here and see if we can work it out. So you look at a 2x2. That's my new purple. Actually, the new purple people seem to like it. I was pleased about that in yesterday's video. So what's it saying? The difference in the positive diagonal. So the difference between this square and this square. So let's just use the example I just did. What was it? 3, 6, 9. So the difference. Oh, that doesn't actually work. Let's try. What was the other one I put in? 3, 4, and 7. That does work. Okay, because here the difference on the positive diagonal within the 2x2. So we sort of are. Let's see if I can do this with a colour. Oh, that's terrible. You look at the difference between those two squares, and the difference seems to be 3. And therefore, the difference on the negative diagonal between those two squares also needs to be 3. Now, in this case, 3 minus 3 is 0, so that's not going to work. But 3 plus 3 is 6. So one possible arrangement of this 2x2 is with a 3, 6 on the negative diagonal and a 4, 7 on the positive diagonal. There we go. What a strange rule. And that's all the rules. So that's all we get. And we all of the arrows are tiny. They're all sort of within, I suppose, they're all within 2x2 regions. Anyway, do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. Let's restart the clock so that we get an accurate time. Now, I say let's get cracking. I have not got a clue what we do here. Let's come back to this one. Let's think about it. So what are we saying? We're saying that the difference between the tip of this arrow and the circle is the same difference as between this square and this square. Okay. I'm sorry, by the way. I don't know if this is that I'm still a bit tired or just that I'm being... Oh, my brain is resisting things here, but I don't really know what that means. I mean, I know what it means in English. I'm trying to detect what that means from a sort of pattern recognition perspective. And I'm not doing very well with that, am I? So this digit is always, because of mathematics, this digit is always equal to the difference between these two squares by mathematics of arrows, because that digit plus this digit equals that digit. So this digit is defining this difference, but then it also has to be the difference between here and here. Right. Yes. So there is okay. So there's sort of a Kropki dot thing going on, isn't there? I might be wrong about this, but I think that this digit, let's make that the purple digit then. This digit has to be either it's either double this digit or sort of, I want to say half of it, but that feels wrong as well, or it's sort of, it's been deducted from this digit. So if this, oh no, hang on, it's always double it, because if you deduct green from itself, this would always be 0. So purple is always double green, is what we've just worked out. That's bizarre. But so does that work? Does that work from here? So are we saying that this digit? Are we saying green is? Let's give that a colour. Are we saying that green is always double blue, and purple is always double green? Because if that's true, then effectively this little sequence here of blue, green, purple is going to be like it's going to be a series of black Kropki dots. Yes, so if that's right, and it may well not be, but let me just pencil in. If that's right, then this is either going 1, 2, 4 or 2, 4, 8, and that's all. So I'm going to delete that because I'm not sure I trust it. I'm going to just let me think about this digit, therefore. So this digit defines the difference between this and this, but on the negative diagonal, this is also defining the difference between blue and this. So yes, so my brain is finally ticking over. So this digit is always double this digit. This is weird. And therefore this digit here cannot be greater than 4. I mean, that's certainly true, because if we were to make it 5, that's defining the difference between the positive diagonal because of maths, and 5 minus 5 is 0 always, and 5 plus 5 is 10, which is always too big to be a Sudoku digit. So this is always 1, 2, 3 or 4. This is always even because it's double this digit, and that logic must survive, mustn't it, for this 2 by 2. It must work the same way. So this digit is always double this digit, so this digit is 4 or 8. And that knocks out this being 6 or 8, which knocks out this being 3 or 4. So we are in a situation where we've got this sort of weird sequence going down from row 1, column 3. Now, what does that mean? Let me think. So, if this is 2, and this is 4, these have the same parity. If this is 1, these have different parity. Okay, hang on. This one, right, there's another of these down here, isn't there? I don't know whether it's going to work the same way when we have a diagonal arrow. That we'll get to that in a moment, but that one, that's definitely the same structure as this and this. So that means that the crook of the arrow here has to be 1, 2, 3 or 4. And this digit must be 2, 4, 6 or 8. So 8 would be very useful here, wouldn't it? Because 8 would have to go with a 1 and make a 9. Uh, 8, 1, 9. The difference on the negative diagonal would be 7. So this being a 9 would make this a 2. Okay, that doesn't actually seem very useful. So how does it work for this then? Is this the same? I'm gonna think about this one. So here, oh, hang on. There's no dot in this one. Oh no. Sorry, ignore everything I said there. I was imagining there was a dot in this 2x2 and there isn't. Oh, that's annoying. So when I said that if this is 8, this is 1, this is 9, and then I looked at the difference between these two, I was assuming I could extrapolate that they had to have the same difference on the positive and the negative diagonal. Now obviously that's not true, because there's no dot in that 2x2. So I'm going to look at this one instead. So let's look at this one. How does this work? So again, this digit. No, it's different. It is different. It is different, isn't it? Because this digit, it's certainly true to say that this digit here, let's pick a better colour, this red digit, it is definitely defining the difference between this domino here. That's how maths works. But this domino is not on the diagonal, so it's a much less powerful thing. So here, the difference between the arrow cells themselves is defining the difference between the positive diagonal on the other side. So the difference between the arrow cells. You know, that feels very unrestrained, doesn't it? So if that's 3 and that's 4 and that's 7, then this has to be 1 different from 7, so it could be 6 or 8. That feels incredibly unrestricted. Let's try a wider difference between the diagonals here. So if we go 1 and 5, that adds up to 6. The difference here is 4, so that would have to be a 2. I'm sorry, what does that mean? Oh, if that was, well, that would, I mean, the thing is, there's no, I don't think there's any restriction really on this. If you go, so the difference between the arrow cells, so if these are both of the same parity, then the difference in the arrow cells is going to be even. This will be even and that will be even. If these are of different parity, then the difference is odd. They will add up to it. Yeah, okay, I've got something. Yeah, this square is definitely even. always, which is quite weird. But I think it's true. And the way I've got that is by thinking about parity on the arrow. So if we think, there's only two basic possibilities for how the arrow works. Either the two digits are the same parity, so they're both even or both odd. And if that's the situation, then the difference between those digits is always even. But they will also always sum to an even digit. So this will always, if these are the same parity, this is always even. And the difference will be even, which will mean this must be even, because we're deducting or adding an even number to an even number. Whereas if these are different parity, they will sum to an odd number, but they will have an odd difference. And when you deduct or add an odd number to an odd number, you always get an even number. So this is always even. Right, so I'm wondering actually if what that means is that this is a parity puzzle. Because if I know those two are even as well, don't I? So blue is my classic even colour because I use blue and orange are our most distinct colours in our palette. So we tend to use so we tend to use orange for odd because they begin with the same letter. So that must be even, because again that's at the crook of one of the, or it's on the diagonal arrows. It's always it's so strange. It's the digit that's not on the arrow, the sort of arrow furniture, that is restricted, or that's the thing I've found so far. So the same is going to be true there. Ah, hang on. So these are both even. So that's even. Ah, this is getting interesting. So it is parity, I think. Now that can't be a 2 or a 4. Ah, because we're adding two even numbers to get to this number. So 4 here would require double 2, which we can't do from a Sudoku perspective. We can't put 8 on the arrow now. So this can't be a 4. Aha, we're finally we're getting somewhere. There must be a 2 on this arrow, because it's got to add up to 6 or 8, and if it was 4 plus 6 it would add up to 10. So there's a 2 on this arrow. It's either 2 and 4 adding to 6 or 2 and 6 adding to 8. But we can't use the, there's no dot here, so we can't just assume that this is even. But if it is even, then all of these would be odd. That would make that odd, because these two are, I mean, this one is just saying that these two digits are the same digit. Now, hang on, let me just find, because I only found 3 of these diagonal. Oh no, this hasn't got a dot. I keep looking at this one thinking it's got a dot, and it just doesn't have one. So we've got 3 even digits in row 5. Now there are only 4 even digits in Sudoku, 2, 4, 6 and 8. So we only need one more even digit in row 5, and we could label all the other digits odd. So if this is even, now the thing is that doesn't matter, does it? If that's even, you still don't know anything about these two. I suppose if either is odd, the other is odd. So perhaps you just know these are the same parity. They're either double even. If this is even, this is either double even or double odd. Yeah, so so if we look at this 2 by 2 here, it's either entirely even or it's got 2 evens on it. So it always has an even number of evens, within that 2 by 2. Now, right. No. Forget all that. I've got a digit. Right. Where? Look at this column. Where's 9 in that column? You can't put 9 on an arrow. And these two apparently can't be 9 because they have to be even. So 9 is there, and 9 is odd, definitely. So that's getting orange. That's our first orange labelling. So I know what I'm going to think about next, but I just want to check whether I can do any Sudoku with this 9. We could... hang on. No, I don't know. Okay, what I want to look at next is where's 8 in column 3, I think. Because if I ever put 8 on an arrow, obviously that arrow is going to sum to 9. So it's going to force an 8-1 pair. So perhaps you can't put 8 on... I don't know whether this is true, but imagine if you can't put 8 on any of those for some reason. Well, actually, even that's not going to do very much. Because this could be 8, and then that would be 9. 8, 1, 9. 1, 2, 4. 2 and 4 here has an even difference. So these have the same parity. What on earth? I'm just going to think about 8 there anyway. So if this is 8, then we know that's 1. We know this is 9. But this is that's a 2, isn't it? That's exactly what we looked at somewhere else. I think it was here when I didn't understand that there was no dot. It certainly doesn't seem impossible, does it? So maybe, okay, let's try something different then. If we could, maybe we meant to look at columns 3 and 4 together. Because each of these little 2 by 2 structures must have at least 2 even digits on it. And in column 3 and 4 together, how many even digits are there in those 2 columns? Well, there's 4 in each column, so there are 8 evens altogether. So there must be 2 here, there must be 2 here, there must be 2 here. But in each of these cases, in each of those 2 by 2s, there could be 4. There could be 4 even digits. And if there was ever 4 even digits, there could only be 1 lot of 4 even digits because the other 2 purple squares would have 2 even digits each, and that would create the 8 evens that we can't go more than 8 evens in the column. So either each of these 2 by 2s has 2 evens on it, in which case there are 2 evens left to place in the yellow squares, or one of the purples contains 4 evens, and if that's the case, the other 2 purples will contain 2 evens and the yellow squares will all be odd. And that's going to matter because if this is odd and this is even, then this is an odd and an even, which is fine. Oh, this might not be right, you know. Well, I mean, I don't think anything I've just said is wrong in terms of logic. I just don't think it's doing anything. I was hopeful. I was hopeful about that. That felt a relatively Phistomefelian sort of thing, actually. Okay, let's try, maybe it's... No. No, sorry, I was wondering if I could apply the same logic in rows 5 and 6, but actually it's worse because I don't have a full 2, I don't have a third full 2 by 2. And actually I don't know anything about this cell because there's, I apologise about this as well, I keep thinking this 2 by 2 has a dot in the middle of it and it just doesn't. So maybe, well, what is it then? What is it? I know there's a relationship between these two squares. This is double this. Wow. How? Maybe there's a reason you can't put 8 into these. I'm going to try that. If you put 8 into the crook, what are we therefore saying? So we're saying this digit can't be very low. Because if this is, say, a 4, that won't work. Because the difference between 4 and 8 is already 4, and you can't make these 4 apart and add them up to 4. So if you put 8 in here, this must be quite a big digit. Now, unfortunately, I think 5 might even work, because then this could be a 1-4 pair. And if this is 6, then these have to be 2 apart, so they're both even, and they're a 2-4 pair. If that's 7, I've just had a horrible thought, this might be able to be 8. But anyway, yeah, this would be a 3-4 pair, wouldn't it? If this is 8, why couldn't it be a double 4 pair in this instance? And it could be, because these 4s don't see each other. Yeah, right. The interesting thing there is, though, that's weird. If you put 8 there, hang on. There is something there, but I don't understand why. I don't understand it. I'll tell you what I've noticed, but I don't understand. When we went through the examples, 5, 6, 7, 8, and 9 there, what I noticed was there was always a 4 on this arrow. So if this is 5, this is a 1-4 pair. If this is 6, this is a 2-4 pair. If it's 7, this seems to be a 3-4 pair. 8, double 4, 9, 4, 5. Why on earth is that? Why if you put, hang on, let me just see if that does anything with different digits. If you put 6 there, what would be absolutely beautiful is that if there has to be a 3 on this arrow now. Now, what's the constraint this time? I mean, obviously, the thing is, could that be very little? It can't be 3 because the difference here can't be 3. If it's 4, then this is a 1-3 pair, and that would have a 3 on it. If it's 5, the difference is 1, and this would be a 2-3 pair. This is weird. 6 would be double 3 because there's no difference on the positive diagonal. If it's 7, the difference is 1, so this would be a 3-4 pair. It would have a 3 on it. If this is 8, the difference is 2, so it would be a 3-5 pair. It would still have a 3 on it. And if it's 9, it would be 3-6, and it would be impossible. That's absolutely fascinating. I don't know if that will hold for 2 and 4, but why? Let's just write 6 in there and think about this. So what we're saying is that whatever digit you put in the opposite circle to create the difference from this digit, it's always necessary to have, it seems always to be necessary to have half of this digit on this arrow. Why? I don't know. I don't understand. It seems to be true. I can't think. I'm not capable of understanding that on the fly. If it turns out that this is generally true, I'm going to think about this after I've finished the puzzle, because that seems strange as. I'm going to keep going with this. If this is 4, well, the pattern we've established seems to suggest, message on the phone, but a WhatsApp message, not an important one. If this is a 4, our pattern would suggest there's a 2 on this arrow. Now, is that true? I don't know. If that's a 9, 2 and 7. If this is an 8, the difference is 4. 2 and 6 works. If it's 7, the difference is 3. 2 and 5 works. This is weird. It's beautiful in a way, but it's so peculiar, isn't it? So if that's 6, difference is 2. This is a 2-4 pair which breaks, but only breaks because of Sudoku. It doesn't break because of the mathematical relationship between the numbers. If it's 5, the difference is 1, so it's a 2-3 pair. If it's 4, the difference is 0. We can do it with a 2-2 pair. If it's 3, the difference is 1, and you can do it with a 1-2 pair, so it's still got a 2 on it. And if it's 2, the difference is 2, and you can't construct a structure that will work. Although 2-0 would work. It just wouldn't from a Sudokuan's perspective in many ways. Okay, let's try it with 2 then. So if this is 2, Oh, that's, well, okay, one beautiful thing I've just noticed is if this is 2 and this is 2, so the difference is 0, that can be double 1. And it would work. So that does suggest this works with 1, so we'd expect half the difference to be on the other diagonal. If it's 3, it's a 1-2 pair. If it's 4, the difference is 2, so it's a 1-3 pair. 5, this is, I mean, it's working, I just don't understand it. This is a 1-4 pair. 6. I feel like I have to do them all because I can't articulate why. 1-5 pair. 7. 1-6 pair. 8. 1-7 pair. 9. 9-1-8 pair. Yeah, so it does work. So what's that doing then? So we've got a new thing that we can try and use for 2x2s where you've got an even digit in the oh my goodness me, right. Okay, well there's one thing I can tell you now which is absolutely beautiful. Sorry, I'm just trying to see if I can see exactly what this does, but I've seen one thing that it does. I can't see it. Oh, well, okay. So what this does, let's look at this. This is where I want to look, and So it's sort of those three digits interacting. This is what this does. Because what we've worked out now is that I was looking at this one, but it applies equally well to this one, doesn't it? So if this is 2, 4, 6 or 8, we know that on this diagonal here we either have 1, 2, 3 or 4, but we don't know which, and we don't know which position it's in. But one of those will have to be half of whatever this is. But that digit, don't forget, also has to appear on this diagonal. So where does it go on this diagonal? If it's in one of those two spaces, so imagine this was 6. We now know there's a 3 in one of those spaces, and we know there's a 3 in one of those spaces. But the 3 couldn't be here, could it? Because it would prevent there being a 3 in one of those two spaces. So it would have to be here, which means these two spaces by Sudoku then, because let's do it with 6 and 3 so you can see what I mean. If that's 6, there's now a 3 on this arrow. There's a 3 on this arrow, which can't be here, so it's here, which means this can't be 3. So you're always going to end up with the 3s in these two precise positions. And that's a general point. So this digit and this digit are always from 1, 2, 3 and 4. And they're always half of this digit. Now, hang on, what does that do? Well, one thing it does, I think, is it means this can't be 4. Because if this was 4, these would be double 2, and you couldn't put a 2 on this arrow over here. So I think we can now take 4 and 2 out of these squares. Oh, come on. Yeah, we could have done that for a different reason, because there must be a 2 in one of those squares as well, because remember this is like a virtual black Kropke dot sequence. This is either 1, 2, 4 or 2, 4, 8, so there is always a 2 on that diagonal as well. Ooh. Yeah, okay, I can get rid of 8 from here. If this is 8, this is double 4, look. And now this is broken. Because this is a 6 by Sudoku, but I can't put 4 on its arrow, so I'd only be able to put 2 and 6 on the arrow, and 2 and 6 do not add up to 6, they add up to 8. So that doesn't work. So this is not 8, and this is not double 4. If this is 2, this is 1, isn't it? That doesn't work for this square. This is beautiful. So this is 6, I think, now, for various different reasons. Ah, Phistomefel, you are a complete genius. A complete and utter genius. So look, if this is 2, this is 1, and that just has no possible options. So this is 6, this is 3, this is 3, this is 8. So we now know that this is a 2-6 pair, and we know that's 6, that's 2, that's 3 by dint of there being effectively a black dot relationship between these two squares. There's a 3 on one of these two squares by Sudoku. There is a 6 in one of these squares by Sudoku. There is no 6 here. Yeah, we've got to do this here as well, don't forget. Because exactly the little trickery that applied in that 3 by 3 applies in this 3 by 3 as well. So these two digits are now either 1s, 2s or 4s. And they are the same, so I'm actually going to label them. And therefore, well, they're not 3, so they go in one of those two positions. The difference between these two digits is 3. So the difference between these two digits is 3. We knew that already just from that one. Oh, Simon, stop being a silly person. Okay, what's this done for us? Have we now broken into this puzzle or not? I'm not sure, actually. These are the same. But there must, okay, but using the fact that we know there's a 2 in one of these, I can't have double 2 here, can I? That won't work. So I can't have 4 here. And again, this can't be a 2-1 pair. This is beautiful. I'm being a bit slow about it, but it's absolutely beautiful. This is now 8, so this is double 4. There's a 4 in one of these two squares. If it was here, this would be 7. I don't know, that might be possible. But this being double 4 has made this a 2, and that a 1, and that a 4. This is one of those puzzles that it's truly remarkably clever, and in a sort of, you know, it's mind-bending what's going on here. Now I've got 2, 5 and 7 to place in these squares, but one thing I can see that's quite interesting is that this can't be 2. So this digit by maths is now 6 or 8 and is even. This can't be 7 because 7 plus 3 is too big, so this is 5 or 8. It's definitely not 6 then, which is one of the possibilities we had here. And this digit, oh, see, sorry, this digit isn't 7 either, because that would be adding to 4. So there's now a 2, 5 pair in the column. So that's 7, that's 8, this is 5, this is 2, this is 5, this is 9. I don't believe it. This is actually going places now. We've done all of a column. We need 1, 6 and 7 into these squares. And, well, let's think about this. The difference between these is even, so these have the same parity. That's not 6. There could be a whole bunch of Sudoku that I'm not appreciating here. This is 9. Oh, it's not. This can't be 6 because this would be 8. So this is 3 or 9. Now it does make sort of sense, doesn't it? But we've got a 1, 7 pair, so that's a 6. And for our next trick, we're going to claim that no, I don't know what we're going to claim. We're going to claim these are both even. So I think these have the same parity. So this digit, just by dint of sort of what it can be from a Sudoku perspective and a maths perspective, is a 1, 2 or a 3, isn't it? Because we're adding it to 4 to create this digit, and it can't be 4 or 5. So it can't be 1 because that would add up to 5. So this it can't be 2 because that would add up to 6. So that's a 3, that's a 7. I didn't do anything clever there, but we still earned another digit or 2. There's a 3 in one of these squares by Sudoku. 1, 2, 6. There's a 9 in one of these squares by Sudoku. So there's a 9 in one of these squares by Sudoku, and it can't be on the arrow. And we can't put 9 here because this would be a 6. So this is 9. Can that be 9? No. No, actually 9 is restricted in box 6, look. Because you can't put 9 here because this would be a 6 by maths and it would clash. So 9 is in one of only 2 places in box 6. So this cell is probably where we're meant to look next. So we've got to add a digit here. It could well be a 1. If it's not a 1, it can't be 4 because that would give 7. Might be able to be 5, which would imply this is 4 or 8. That's the only, I think that's the only option. So that is even. Actually, maybe I should have kept up with my parity shading. I've neglected that a little bit, haven't I? So this is either a 1-4 pair or a 5-8 pair. If it's 5-8, 5 and 8 live up here. I'm not seeing how to resolve that, am I? That's 4. This is 1. The difference here is 2. The difference here is 2. I mean, it all works sort of from a diagonals perspective. Therefore, what are we therefore saying? Oh, I see. Right, beautiful. This can't be 6. Because if it's 6, how do we create a difference of 4 on its arrow? And the answer is you can do it, but it's going to use a 1 and a 5. And that won't work, because there is a 5 here that sees both of those squares. So that can't be 6, which means this is 6. It might not do much for us, but that is certainly a truth. So there's a 6 up here now. And because this is a 2, remember our rule, we know there's a 1, don't we, in one of these two squares. So there is a 1 on the arrow. But I don't know what that means. There is a 1 on this arrow. If this was a 1, that would be 5, 8, and that would be 7. And this would be a 1. If this is 3, then we know this is 1, so it would be 3, 1, 4. Something here doesn't work, but I don't know what it is. Maybe we've got to be a bit more diligent and just pencil mark it. So if that's 3, is that possible? No, because that will be a 1, 2 on the arrow, and this 2 sees everything. So 4 seems to be possible. 5 and 6 don't work by Sudoku. 7, does that work? That's going to be a 1, 6 pair. No, you can't put 6 on the arrow, so 7 doesn't work. 8, that's the only other option. This would be a 1, 7 pair. So this is either a 1, 7 pair or a 1, 3 pair. And that's never 3. So I've now got a 1, 7 pair, actually. That's very strange. In box 5. How do we restrict this digit? So these digits are the same. Oh, we must be quite close now, I think. How do we... I know there's a 1 in one of these positions. I know these two digits are the same. So, maybe I have to Sudoku these. 1 seems possible. 2 is out. 3 is possible. 4 is out. 5, 6 are out. 7, 1, 3 or 7 into these squares. That's all that works. So there's something going on, isn't there, between, I think, this arrow or this diagonal and this arrow here. I mean, actually, it looks likely these are going to end up being 3s to me. And then this would be a 1, 7 pair. This would be an 8. I don't know. It doesn't... not sure. So we are still left with a conundrum, I'm afraid. We're going to have to think of something else to do. 1 in box 2. I don't know where it goes, but it's in one of those 3 places. And we know 1 in box 5 is in one of these 2 places, so we can think about 1 in the middle column. It's not in any of those 6 cells, so 1 is in one of those 3 squares. I mean, it's probably not important, but it does seem to be true. Oh, I don't know. Shall we try this digit? Is that under any pressure? I mean, we're running out of places to look. We've got to find somewhere to look, don't we? I suspect that this is not going to be terribly fruitful, but I'm going to try it. The difference, obviously, on the arrows is 3. So let's put in the options. So this is at least a 4. So this is 4, 5, 7, or 9 by Sudoku. Can we restrict that any further? I don't know. So this is 1, 2, 4, or 6. It's not 6 because of this, so this isn't 9. So this is 1, 2, or 4. And this is 4, 5, or 7. Wow. Oh, what am I missing? I don't know. 2 is in one of those 2 squares in box 5 by Sudoku. This is either a 1-3 pair or a 7-9 pair. If it's 7, 9, this would be a 9 in box 5. This would be a 9. And that would mean this would be a 9. So 9 would be a bit restricted in box 3, but I don't... Oh no, it would be up here, wouldn't it? Doesn't look terribly bad. If I know one of these squares is a 1, and I do know that, has that... Ah! No, that's not... Oh, I suddenly thought there's a 1 in one of these. That's not true, though, is it? Because the 1 could be here. So if this is a 1, then this is a 1. Which doesn't necessarily mean this is a 1, but might. Okay, well, I'm a bit baffled as to where to, I don't know where to look at all. 1, 3, 7, 4, and 8. So, is it Sudoku? I mean, that would be a terrifying prospect. Is there anything else I can see? It could be... I know those 2 digits are the same. Is there a one of these arrow things I've not used? That's also very possible, isn't it? Because there was a whole flurry of activity when we got lucky and we were able to do some things. But I could well have not exploited those things fully. Let me see. Oh, there's a siren going off outside. Or is it the fact that I've effectively got 5 digits in box 5? I haven't used 2, 4, 8, and 9. So, but I know that 4 is already restricted. Is there some sort of contradiction with 4s then? If this is 4, this is 4, this is 1, so this is 1, and that doesn't work. Ah, so it's something to do with 4s. I just have to understand it. Yeah, I mean, it's true. I mean, if this is... The point is this can't be 4, but it's just quite difficult to see this. So let me show you. If this is 4, because of where 4 has to go in box 5, it has to be here. Now, but this is a 1 now by the maths of this arrow. And we know there's a 1 on this arrow, which has to now be here by Sudoku. But this can't be a 3 because of this 3. So the world breaks down. So it's very clever, but it's hard. That was difficult. That's difficult. So that becomes 8 and that becomes 5. And I'm not even sure that's going to do very much. I hope it does. Well, no, by Sudoku it does, because it places 8 here in row 4. And therefore we know that this is a 1-7 pair, because we know there's 1 on the arrow. And therefore we know that this is a 3 and it mimics itself here. So this did become double 3, which is what we suspected it might become. And that's going to mean, oh, nearly, there is a 5 in one of those two squares. And if this is double 3, well, we probably, one thing we ought to do, we do know that this is a 4 now, don't we? So that's 4, that's 2, that's 9, that's 3, that's 1, that's 7. Oh, this is beautiful. Good grief, look at all that flurry of activity. Now, 4 and 7 are looking at this arrow, so that's a 5, which means this is a 2. Let's check the differences are working. They are. This is now 4, because we have to have a purple digit here somewhere. Oh, this is great, isn't it? Because now, oh, that's a 9 by Sudoku. So this should be, oh, we need to put 1 and 4 into the box, and we can do that. So this is 1. This is 4 and this is 7, and the first, well, the middle 3 rows are done out of absolutely nowhere. Now we can say, what should we say now? I don't know. How many arrows have I got left to use? It looks like none. We've got that sort of little configuration that we've not even thought about. So there must be a lot of Sudoku we can do at this point, is what I'm hoping, because otherwise it's going to get very tricky. Where is 3? There are 4 3s looking at box 1. And that means that this is a 3. And that means that's 3 in the corner, that's 3 in the spotlight, losing its religion. Okay. So 5 and 8 now in this box have to be here, don't they? By Sudoku. So these are 2, 4 and 6. Which looks to me like it might be chocolate teapotted, unfortunately. But it does mean that this square here has to be a 1, which has probably been available for a while. 6, 7 and 8 into this row. So the 6 must go here by Sudoku because of this 6. The 8 must go here, the 7 must go here, the 7 must go here. These squares are now ones, oh no, what are they? 6, 9 and something. 5, 6 and 9. These are 2 and 3. We can place the 3. These are 1 and 5, which apparently we can't do. What are these then? 2 and 9. Well, we can do that. So, what does all this mean? I'm not sure yet, but it must be getting close. Now this is... How do we do some Sudoku up here? Not sure. Should we have a look at column 7? 1, 5, 6 and 8. Let's fully pencil mark it and hope. That's not 1 or 8. What's going on down here? This is not 8. This is not... Oh, it doesn't look good enough. It doesn't look good enough. Oh, that's distressing. So we are probably going to have to use this green thing at the top. So how does that work? We might have to sort of do Sudoku and work out what has to be in it, if anything. 4. There has to be a 4 in it, in one of those two squares. Oh, I thought there had to be a 2 in it, but that isn't true. There could be a 2 in it, but there needn't be. Wow, 2, 5, 6, 7, 8. Sorry, I'm just trying to work out what it is. There is a 7 in one of these squares. And we're trying to work out how we're ever going to solve this, or what the constraint is in this 2 by 2 at the top. It's not immediately apparent to me that there's no arrows here, so all we're saying is that these two squares have the same difference as these two squares. I mean, I'm wondering whether I'm actually going to have to pencil mark them fully, because I'm not using this sort of corner pencil marking method. I'm not really getting anything there that looks like it's going to be good enough. I mean, that might be wrong, but I don't know. I mean, this digit has to be quite a high digit because it sees all the low digits. So that digit is 6, 8, or 9. So if we knew that this, what do we want this to be then? If we knew that this one was, well, it looks like it's going to be quite high as well, because it can't be 1, 2, or 3. So it is 4, 5, or 9. Yeah, so that diagonal is a little interesting, I think. Perhaps. Let's say perhaps. Okay, well, let's keep going with this then. So what do we have to put in the top corner? I think there's a lot of possibilities. 6. Well, okay. If I've got that right, it's only 2, 6, or 9. Let me check that again. Yeah, I think 2, 6, or 9. So if this is not 4, this becomes a 4, doesn't it? Because of our pencil marking. So maybe we can do something with that. So if this is 9, the difference on this diagonal is always going to be 1 or 3 then. But this is always going to be 4. And that cannot have a 1 or a 3 difference with any of the options here, which are 2, 6, and 9. So I'm going to claim this is not 9. That felt right. So maybe we can prove this. So if this is 5 now, that's going to be 4, isn't it? But that's going to be 6 as well. So everything's going to get very constrained. In fact, that's going to go 5, 6, 9. So that's going to have to be 2. So if this is 5, the difference on this diagonal, it doesn't work. Because if this is 5, I think, let's just take this very slowly. If this is 5, because this is a 6, 9 pair, this is a 2, but this is a 4. So the difference on this diagonal is 2, but this is 5, so this needs to be 7 or 3, which doesn't work. So I think we end up with this being 4, which is probably not going to do anything. Let's see. It does give me a 4 here, but it doesn't look like it's a useful 4. Oh, come on. You rotten thing. You rotten thing. Right, so we have to pencil mark this digit, don't we? This is 1, 5, or 9. Okay, that is more restricted than I was imagining. And we know the difference on the positive diagonal is 2, 4, or 5. How could we? Oh, we can create a 5 difference. I've seen a way with a 1 and a 6. So I can't immediately rule that out, which is a bit disconcerting. What we can rule out, slightly strangely, is that this can't be a 6, I don't think. Because the difference then on the negative diagonal is 2. And there is no way of having a 2 difference between these options here. So that is not 6. Now if this is 8, we've got a 4 difference. How are we going to do that? We could have a 5 and a 9. So we can do that. Bother. Bother. Sorry, I thought I'd seen something there, but I haven't. I think that's the only way of doing it, is with 5 and 9. And if this is 9, we've got a 5 difference, and then this is 1 and 6. So this is either a 1-6 pair or a 5-9 pair, which would mean this is never 2. Perhaps that's the point we're meant to get to. Yeah, let's think about that. So can this ever be a 2? I think not, but I'm not 1,000,000% convinced. If it's 2, we know the difference here is 4 or 5. So this has to be 6 or 7 and can't be. Yeah, that's fine. So this is not 2. So this is 2, which seems to mean that's 7. That's 2 and that's 6. So this is 5, this is 5 and this is 8. Now, that's done quite a bit of Sudoku for us. Has it done enough? It's knocked 5 out of these squares. We've got a 6-9 pair in the top row, so that's become a 5. These lose their ability to be 5s. Maybe Sudoku will help us in this column now. 1, 5 and 9 to place. So I've got a 1-5 pair, there we go, that's useful. So that's done something. And the 1-5 pair means that this becomes a 7. This square is an 8 or a 9 in the corner, which actually that's useful. Is that definitely right? I think it is. So we can only put 6 in one place in the column. So that's 6, that's 9. And now we know that we need, well, once this was 6, this has to be 1, because we can't create a 3 difference on this diagonal. So this is 1, this is 9, this is 8. Now, does this unwind, though? So we need it now to work. Oh, it's going to work, isn't it? Of course, it's Phistomefel, it's going to work. There we go. What a puzzle that is. Yes. What? 117 people have solved that in about a month. Okay, so I'm very late to it. That is a brilliant puzzle. It's fascinating, actually. I need to think about it, because the thing that we noticed about these diagonal arrows that have, it's this square in the diagonal arrow with a dot, and then you have to put half of the difference onto the arrow, is so strange to me. That's just weird. And then the fact you could use these little congregations of them to make these 2 digits the same was utterly, utterly beautiful. Phistomefel, you are a total genius and a lover of great music. And I love your puzzles. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.